Welcome to this video presented by the Society of Mechanical Ventilation. Modes of Mechanical Ventilation, Flow Control Ventilation. Presented by Mr. Marco Clausen.
Well, hello everybody. Welcome to this episode of the Society Mechanical Ventilation. Today we're going to talk about a mode, kind of newish mode. It hasn't been there for too long. I don't know much about this mode because I never used it. So we have all the information right from the source. I have my dear friend Marco Clausen from Ventinova in Netherlands, and he was going to tell us all about it. So Marco, welcome and thank you for being here. And just please introduce yourself and take it from here.
Thank you so much, Eyap. As you know, it's a privilege to meet you in person. I'm a big fan of the Society of Mechanical Ventilation, not only because of the content, the very easy, approachable content, but also because of the friends I met, all ventilation enthusiasts, which connected our to Society of Mechanical Ventilation. And of course, thank you for the introduction and for the invitation to explain this quite new ventilation mode, just like you say. Just 2017, we started with introducing the Yvonne, and we started to explain this new way of mechanical ventilation. I cannot otherwise say it, because until now it's quite interesting. We mainly focused since the polio pandemic, since the 1950s, we mainly focused on the inspiratory phase. We give pressure during the inspiratory phase, and then afterwards we rely. The exhaust valve opens and we have to rely on passive backflow, based on patient physics, on compliance and resistance. And it's very strange because the respiratory cycle, the half of the respiratory cycle, is the expiratory phase. And we only can control this a little bit with PEEP levels. So if you can control also the expiratory phase, it gives you a lot of new opportunities. But it's quite difficult. It's an absolutely different ventilation method than pressure control and volume control. So flow controlled ventilation is based on continuous, very low, linear and stable, identical flows, not only during the inspiratory phase, but also during the expiratory phase. It's like a pyramid. And if you look to the curves, because we like to use very low flows and an equal inspiration expiratory time. So if you look to the intratracheal pressure curve, the flow curve, and the volume curve, during the inspiration, there is a linear increase until your peak pressure. There is a continuous flow during the inspiratory phase, and there is a stable increase to your maximum inspired tidal volume. But now, during the expiratory phase, this is absolutely different than in conventional. Also during the expiratory phase, there is a linear gradient to your anexpiratory pressure, from peak pressure to anexpiratory pressure. So you avoid excessive pressure drops when cycling from the inspiratory phase to the expiratory phase. This is one benefit. And that's all done because you can control the flow during the expiratory phase. There is also a continuous flow during the expiratory phase. And this means a stable gas flow from your maximum inspired tidal volume until your unexpired tidal volume. And because you can control the expiratory phase, you can always work with an A ratio 1:1, as close to as 1:1. And this levels more or less the fast time long constants and the prolonged time long time constants. So you level more or less all those different situations inside the lungs. And if you compare flow-controlled ventilation with volume-controlled ventilation or pressure-controlled ventilation, and you look to the pressure to the curves, and you see the linear decrease of pressure, the continuous flow, and a linear decrease in volume controlled ventilation, pressure controlled ventilation. First, you have pause phases, which you don't have in flow controlled ventilation, but moreover, you avoid those upward pressure drops during the cycle inspiratory phase to expiratory phase. And even more, there's a totally different way of expiration, where your expiratory flow normally is based on physics, how fast your expiratory flow is finished, how long your time is to exhale. In flow control ventilation, you can control this in a much more easy way. And this is how you set the EVONE. There's only 5 buttons on the EVONE, so it's quite easy to adjust. But you need to understand physics, and you need to understand how the ventilator gets gas flow and how to deal with the expiratory phase. And there is one FU2 button, and the FU2 button you set the same as in conventional, based on oxygenation. But now it's quite different. This, we call it EEP, or we name it EEP, because you can set your expiratory pressure also negative, and you control the expiratory phase. You can induce a negative intrathoracic pressure. And this can be very helpful for your intrathoracic blood flow. And it's now under for research, for resuscitation, but also to reduce your intracranial pressure. The other one is your peak pressure. So these buttons, you estimate or you set your driving pressure. And that's a dark blue line. And you always ventilate in between those pressure limits. And this is also a difference between a conventional, where conventional, you adjust your minute volume by frequency and tidal volume. Here you do the opposite. This is a flow button. In this case, 10 liters of flow. And because you can work always with an A ratio 1:1, this means the half of your flow will be your minute volume. So you can preset your minute volume by increasing or decreasing the flow. Your tidal volume will be the same. And this is an example how it works. So now I have an inspiratory tidal volume of a flow of 10. This means a minute volume of 5. If I should increase my flow to 15, there is more air going to the patient. This means with the same patient characteristics, compliance resistance, I will reach my peak pressure in a more early state, and EVONE cycles directly to the expiratory phase, this part. And when he hits the EEP, the expiratory pressure, he directly cycles to the inspiratory phase. And this is how the EVONE works. So your flow, you adjust your minute volume, but because there's more flow going to the patient, the frequency will also increase. And then you see this sort of curves. On the other hand, so this is how you adjust your minute volume to control your end tidal CO2. On the other hand, you can also adjust your tidal volume by increasing your driving pressure. So for instance, if I have the same flow, the same patient characteristics, and I increase my peak to 20, so I increase the dark blue line, you have more time to go to that peak pressure. So there's more flow, there's more air. It takes a longer time to reach the peak pressure. So my tidal volume will increase and my frequency will decrease. And this is how you adapt to physics. Without any pause phases. So there is continuously dynamical gas flowing. And very low flows. The EVONE only works with a maximum flow of 20 liters a minute. When you're in volume control, maybe you have to use 40 liters a minute, 60 liters a minute. We go maximum to 20 liters a minute. And this gives a totally different way of gas distribution. And you see now the frequency goes down and your tidal volume will increase. And about gas flowing, to reach the fast time constants, slow time constant, this is a very important concept, which in my opinion sometimes is neglected. If you have a driving pressure, or I don't name it driving pressure, I set tracheal pressure set on the Yvonne. Let's say a peak pressure of 24 and a EAP of 8. So I have a pressure set on the Yvonne of 16 in all cases. But now I have a resistance here, a low resistance, a moderate, and a high resistance. This means with the same driving pressure, only an alveolar driving pressure of 14 is left in the low airway. But in the higher airway resistance, you need 8 centimeters of water, 8 millibar, just to overcome airway resistance. So only the half is coming to alveolar pumping, is coming to the alveolar driving pressure. But this is with a flow of 8 liters. If you have the same settings, and I just only increase my set flow in the same situations, you see here already the pressure needed to overcome resistance is doubled. But here in the high airway resistance, there is no alveolar pressure left. So in other words, there is no alveolar pumping. For COPD patients, it's very common to increase tidal volume or increase respiratory rate. This means less alveolar pumping. So what we do sometimes in high resistance patients, we reduce the flow and we have better alveolar pumping. Just to show you the influence of resistance on flow. And this also means the dynamic, and you know much better than I do, the dynamics on alveolar level are very depending on the balance between compliance and resistance. So do we find the Holy Grail? Are we not more going from statical measurements to dynamical measurements? And of course, I would never question the importance of volume, importance of pressure. But these are all statical measurements. It's not depending on FRC, the 6 ml, the baby lung, the 6 ml ideal body weight. And so maybe we have to go much more. And again, Ian, you are a pioneer on this. We have to go much more on alveolar stress, on alveolar strain. And not only this, very important is to do that in time. And more is repetition, respiratory rate. But also mechanical power is estimated in 1 minute. But not in a day, not in 5 days. How long do you ventilate? And if you can manage to the inspiratory time, the expiratory time, and have the longest inspiratory phase and the less air movement, the less lung movement, that will surely benefit. So we are more going to dynamical stress and strain in time. And this is all viscoelastic material. If you squeeze very gentle on the can, it will not break. If you do that 4 times, it breaks. It will not go back to the normal position. The same counts for chewing gum. If you stretch very slowly on the chewing gum, it will not break. But if you do it fierce, it immediately breaks. So it has all to do with how fast things stretch, how fast the strain, how much strain is put on the subject. So time is a very important factor. And this is the CT scan after 10 hours, where FCV is compared with PCV. And now you see the benefits of the low flow, the benefits of keeping the lungs open, not the collapse during the expiratory phase. And you see less atelectasis in FCV compared to PCV, just keeping the lungs open. And this is the dynamic CT scan. And also here, you see a better aeration, especially in the depending lung parts. And research states there is 30% less minute volume needed for the same end-tidal CO2, to maintain the same end-tidal CO2 level. So this has impact on mechanical loads, on ventilator loads, on repetition, so also on lung protection. And if you look to the PV loops, if you look to the histology, but most interestingly, the PV loops, they are very small PV loops, reflecting also the dissipated energy, much smaller than VCV, PCV. So you see a very small PV loop. And these are some papers already published. And also here you see a significant reduction of minute volume, and therefore also a significant reduction of mechanical power and dissipated energy. And this is an ICU patient post-cardiac. And because you have a very stable flow pattern as well inspiratory phase, expiratory phase, and you measure the pressures deep tracheal, we have a special probe which measures the tracheal pressure below the tubing. And you have a very stable environment. Also, your PV will be much more accurate. And this is how you can optimize based on the compliance curve. And if it comes to gas exchange, also here, this is in RDS patients, a very short period. But also here, you find a lower minute volume required for the same pH CO2 levels. So there must be a difference in gas exchange, in gas distribution. Otherwise, you don't get these results. And not to forget on hemodynamics. The influence of very stable intratracheal pressure swings in combinations with your cardiac output in your intratracheal blood flow. Maybe this also improves the ventilation perfusion. And there are already studies who show that. But also in obese patients, if it comes to keeping the lungs open, especially in the depending lung parts. And so FCP better maintained and expiratory lung volume, just by avoiding collapse, just by keeping the mean airway pressure a little higher. A different way of ventilation. And here, these are some pictures. If it comes to diaphragm swings, if it comes to organ movement, we bring the Evone to the radiology, interventional radiology. So now you can ventilate without any pause, and you can still do an ablation, a liver ablation, for instance. Just because the organ movement is much more efficient controlled. This was in the COVID pandemic. I have to say, because the limitations of the Evone, one of the main limitation is the patient cannot trigger to the high compliant system. The low compliant system with a high resistance. The breathing system is simply too small. The inner diameter is too small to exhale and to trigger to the system. I will show you the tube and the breathing system afterwards. So the patient has to be sedated and is not allowed to trigger. But here, if it comes to cardiac surgery, to balance the interference of the lungs into the surgical field, this is ex vivo lung perfusion, just for keeping the lungs open and to minimize stress and strain. These are quite difficult to prove, except of course the ablations, because you go to mortality, you come to ICU stay, so it's much more abstract than, for instance, organ movement that you see immediately. Now there's a very nice project ongoing on robotic surgery. And in this case, you try to avoid the excessive diaphragm swings and also the excessive expiratory flows. So just also to keep the lungs open. And what we are really, or still are a big player now, is in a small lumen ventilation. And you can imagine, if you don't control the expiratory phase, it's impossible to ventilate with small bore lumina in a totally obstructed airway. You cannot use a cuff. Jet ventilation needs an open airway to exhale. But if you control the expiratory phase and you can manage to get the air extracted to an inner diameter of 2 millimeters, you can use small bore diameters without the chance of air trapping. And if you should use a balloon or a conventional device on these sort of diameters, this will never work. You will immediately hyperinflate the patient. But if you control the expiratory phase, you can use an inner diameter of 2 millimeters. This one is 2 millimeters. And this one is 2.4 with a cuff. So you don't need an open airway. For jet ventilation, you need an open airway. This means backflow. This means you cannot measure your end-tidal CO2 continuously. You cannot have your readouts. You have not your PEEP level as you would like. So below an inner diameter of, let's say, 3 millimeters, the acceleration time exponential will increase to more than half a minute. So you need a control of expiratory phase. And when it comes to a shared airway, when it comes to small lumen ventilation, this is a very nice case from Dr. Nabil Shalik. He is really expert in FCV, and he could manage to introduce the tube to that stenosis, and therefore they avoided an ECMO. And the surgeon can work perfectly around the tube, so the surgeon has also the benefit. And this is even more interesting. So now you can ventilate this small lady of 3 kilograms, could not be ventilated another way because there was a trachea malacy, and the opening was too small to rely on a passive backflow. And this is an elective patient, so it's a very not invasive method. You ventilate, you optimize the patient, and now you can work the whole procedure. You can do it like this in an awake patient. And this one is also done by Dr. Nabil Shalik, and he started with optimizing with a front of neck colectomy needle, and afterwards by his Seldinger technique, he introduced the tube. I will show the tube later. He introduced the tube, he inflated the cuff, and he had a fully secured airway without interfering the surgical field and without a difficult intubation. And after the procedure, just put a plaster and the patient went to the ward. And this is in tracheal stenosis. This is also the shared airway, small lumen ventilation. So now you don't need any crossover intubation. You don't have the backdraws of jet ventilation. You inflate the cuff, you have a secure airway, and the surgeon can work around the whole procedure. So you don't need to do a re-intubation. And this is also a very interesting case. This is to change for ICU patients in an early stage where you need PEEP, where you don't want to lose the airway. You introduce the tube towards the conventional tube. You withdraw the conventional tube. You inflate the cup of the tube. Now you have a secure airway with all your readouts, your minute volume, everything you have. And then you have all the time to introduce by the Seldinger technique the trachea cannula. And then you remove the tube, and now you have changed from the conventional tube to the trachea cannula. And finally, some studies, ongoing studies. This is a multi-center study based on the expiratory flow of expiratory control in robotic surgery. And this is also very interesting. This is done now in Erasmus Clinical Academical Center in Rotterdam. And they compare flow control ventilation against volume control ventilation, obstructive and asthmatic patients. Just to look if the hyperinflation, if you can avoid or if you can treat hyperinflation in a more efficient way. And finally, this is a very nice lecture which explains in a very nice way the interaction of stressed lungs and the mechanical power, the influence of flow, of stress and strain on repetition or acceleration on stressed lungs in a very nice way. Whoa.
Yeah, I saw this lecture and it's really, really good. I recommend it to everybody. Like in the...
Yes, even I did understand it. It's very difficult mathematical stuff, but even I did understand it, so that means a lot.
Yeah. Marco, that was very, very, very cool and great. Really, you explained it very well. Really appreciate that.
I hope so.
Yeah. I don't know if you still have more slides or...
No, I think this must be enough. I think this must...
You're going to show us the tubes? Okay.
Yeah, maybe this is nice to show you the tube. So it's called tube. You measure the pressure deep tracheal by the black. So you have to measure the pressure below the cuff because it makes no sense to measure the pressure above the resistance. And now you have a total flexible tubing. So this is for shared airway and for emergencies, so you can also use it front of neck. And this one is for conventional, to connect to the conventional tubings. So also here you have a very deep tracheal pressure measurement. So you put the catheter inside the tubing, and now you measure also, independently of the diameter of the tube, you measure the intratracheal pressure. So this is the two different ways to ventilate.
So this is the true tracheal pressure, because most of the ventilators now just estimate the tracheal pressure, and yeah, so that makes much more sense.
And I think you know better than I, if it's efficient to have all your measurement only on the ventilator. I think that's another question, if it's enough to measure only on the ventilator. But I'm sure if you have to measure, and in the Netherlands, for instance, I think only 5% of the hospitals use transpulmonary pressures, and maybe less, they use EIT. So there is no other option.
Great. Do you have a couple of minutes? If you're done, I have some questions I would like to ask you. Whenever you're done.
Not too difficult, you know.
No. No, I just didn't want to interrupt your presentation. It was a really great presentation. Thank you. No, so you said, like, of course, the patient cannot have spontaneous breathing because of the issues that you mentioned. Makes sense. How long, or what is the longest you ventilated somebody? Like, usually for bad ARDS, you recommend like maybe paralysis for 24, 48 hours. When do you switch from flow controlled ventilation? You want to wake up the patient, you want to wean them and stuff like that. First of all, how would you change the tube back to a regular endotracheal tube?
Normally so we don't have to change the tubing, because for long patients who have to ventilate a long time, we just use the CTA adapter. So we don't use the small lumen ventilation, because the secretias will be blocking the tubing. So we use, for ICU, we use a normal bore tubing.
Oh,
And then it goes more to gas exchange, and then you just switch the ventilator.
Okay.
Normally it's for 72 hours, so it's stated for 72 hours. But the biggest limitation, it needs undivided attention. You cannot afford to let the patient trigger and you don't see it. So if you have a very nice physician who wants to sit in a chair for 3 days besides the patient, you can ventilate for weeks. But that's the limitation. So we are working now on a solution to let the patient trigger along the ventilation system by a valve, or adapt in a better way the flow to the patient. So we need to find a way to let the patient trigger, because that's the biggest limitation to go to the ICU at the moment.
To avoid the weakness and diaphragmatic atrophies and stuff like that.
Exactly.
Okay, very good. How about, so when the EEP, because it's a very, very interesting concept, and I didn't know that, I read about flow control before, but I didn't know that you can set even the end expiratory pressure to negative, which is pretty cool. I mean, the problem with positive ventilation, as you know, is it's totally unphysiologic. So if you can take the expiratory pressure to the negative, that's very, very cool.
Yes,
When did you do it?
Yeah, and now there is a very nice paper just published, and it states when you set a negative pressure, I believe a negative pressure of 9 EEP, 9 EEP, it will reduce the intracranial pressure significantly. So if you go to a brain trauma, it will be very nice. Also for resuscitation, to reduce the right ventricle afterload, it will be very nice. You can also imagine if you can compare your decrease of intratracheal pressure with your cardiac output. That is also a very interesting investigation. And also there is a paper published, you need less noradrenaline for the same patient, just by controlling intratracheal pressures. But this is just a start. So we need
Okay.
more pioneers.
Yeah, no, this is
Because
great.
you cannot do this, or maybe you can do. We don't know, because to set a negative pressure will surely also have influence on your atelectasis. But a -9 is investigated at the moment. And
And what's the, oh,
so
sorry.
it gave a significant difference in intracranial pressure, much better than volume control.
Yeah, yeah, makes sense.
Normal people.
And what's the highest end expiratory pressure you used?
The highest,
Yeah,
I think that's around 10, 12.
okay.
I think that's around, but also this is a very interesting question. Do you go more for the higher PEEP levels or for the lower PEEP levels? I believe
Right.
it's depending. That's also our philosophy, to have individualized ventilation. I think it depends very on the patient. Very on the
Totally,
patient.
totally agree.
But
Yeah,
what we know is this is a dynamical pressure. So the EEP is dynamical. So during the inspiratory phase, the driving pressure, the pressure on alveolar level must be higher than your EEP. But during the expiratory phase, it always must be a higher EEP compared to your settings on the ventilator alveolar EEP. Because otherwise there's no gas flowing.
yeah, it's very, very interesting. And I think like having some studies with EIT or even measuring with esophageal balloons to see, it would be very, very interesting,
Interestingly, the EIT is quite common use now in combination with the FCV, but the transpondable pressures are not. And
Yeah,
only, as you stated so nicely many times, the volumetric capnography.
right.
Those combinations of EIT, transpondable pressures, and volumetric capnography, that would be a very nice, interesting combination. With artificial intelligence, of course. That's also a route we make now.
No, I mean, you guys have like a really good start, and I'm sure everything is just gonna keep going better, and we know more and improve things, so that's great.
Yes, it's really a journey. It's really a journey to start somewhere.
Yeah.
Professor Enk, I have to mention him. Professor Enk was the one who started to think, okay, we have to control the expiratory phase.
No,
So
thinking out of the box, that's great.
exactly. That's this.
Yeah. All right, Marco. Well, I'm really grateful for you spending the time and taking
No,
your time to like, help us understand that mode. I really appreciate it.
the pleasure was totally mine. Thank you so much.